Hello friends, welcome to my channel. We are going to introduce convex sets. In the first figure, if we join any 2 points, the line segment joining 2 points lies wholly on the figure. But in the second figure, if we join any 2 point, the line segment joining 2 point does not lie on the figure. So the first figure is categorized under convex sets and second is categorized under non-convex sets. So again we are going to define in formal way what are the convex sets. Let X be a subset of Rn. X is said to be a convex set if for every A and B in elements of X and lambda is the real number between 0 to 1, lambda A plus 1 minus lambda B is also belongs to X. So we have two examples. The empty set and singleton sets are convex sets. Why? Since if there is no any element in empty set, so their combination of elements does not lie in empty set. So this is trivial. And for singleton sets, we have taken a singleton set X and X is the element of Rn tuples of Rn and lambda equals to 1 upon 2. So lambda A plus 1 minus lambda B, here A and B are same. So X lambda X plus 1 minus lambda X equals to X, and since this also belongs to A, so A is a convex set. So again we are going to move for another example. The second example is we have taken a ball B X in Rn such that norm of X minus X naught is less than or equals to epsilon. Epsilon is greater than 0. Is also a convex set since this is a sphere, and if we join any 2 points in a sphere, the line segment lies wholly in the sphere. So this is a convex set. Again we have a proposition that first, if let X and Y be the subset of Rn, be two convex sets, then their sum X plus Y is also a convex set. Second, the second is if C is any real number, then Cx is also a convex set. For X is a convex set of Rn. Again we are going to prove. First, let x1 x2 in X and y1 comma y2 in Y, let and lambda lies between 0 to 1. So x A equals to x1 plus x2, A equals to x1 plus y1 in X plus Y, and B equals to x2 plus y2 is in X plus Y. So since X is a convex set, so lambda x1 plus 1 minus lambda x2 lies in X, and lambda y1 plus 1 minus lambda y2 lies in Y. So the sum of two lambda x1 plus 1 minus lambda x2 plus lambda y1 plus 1 minus lambda y2 lies in X plus Y. Again lambda equals to lambda into x1 plus y1 plus 1 minus lambda x2 plus y2 lies in x plus y. Again, what this becomes? This is lambda a plus 1 minus lambda b lies in x plus y. What we have shown? We have shown that for every a and b in x plus y, and for every lambda between 0 to 1, lambda a plus 1 minus lambda b is also in x plus y. So this is the definition of x plus y. Since a and b are arbitrary numbers, so this is true for any real numbers, any numbers of x plus y. So x plus y is a convex set. Convex sets. Again, we have a problem that prove or disprove that union of two convex sets may be convex sets. We have may not be convex set. So we are going to check this statement. So first of all, take two convex sets, a equals to 0 to 1. This is a closed set, so this is a convex set. Since this is closed, and b equals to, take 2 to 3 is also a closed interval of R, so is also a convex set. Again, if we join any two real numbers by lambda and 1 minus lambda, this lies wholly in a and b, so these are convex sets. Again, we can check it. This is trivial, and what we do, again, a union b equals to 0 to 1 union 2 comma 3. Take a equals to 1 in a union b, and b equals to 2 in a union b. Again, lambda equals to, take lambda equals to 1 upon 2. So lambda a plus 1 minus lambda b must lie in a union b. So lambda equals to 1 upon 2. We have taken 1 upon 2. This, since this is between 0 to 1, so again 1 upon 2 into 1 plus 1 minus lambda into 2, and this is equals to 1 upon 2 plus 1 upon 2 plus 1. This is 1.5, and 1.5 is a real number between 1 and 2, and we have seen that the real number between 1 and 2 does not lie in a union b. So we have shown that, we have checked that 1.5 does not lie in a union b. So we have, what we have found? We have found that if a is in a union b and b is the element of a union b, then lambda a plus 1 minus lambda b may not be element of a union b. So a union b is not a convex set. So a union b is not a convex set. So we have shown that the union of two convex sets may not be a convex set. Again we have a theorem. What is the theorem is? The theorem is about the intersection of two convex sets. Let S alpha be the family of, alpha is a family of sets, be a family of convex subsets of Rn, then intersection of these sets is also a convex subset of Rn. Convex subset of Rn. So proof of this theorem is very simple. So let A and B in intersection of these families of sets, and lambda lies between 0 to 1. Again, so since A and B lies in the family of intersection, so A and B lies in S alpha for every alpha in I. So S alpha, since we have known that S alpha is a convex subset of Rn for every alpha in I. So again, lambda A plus 1 minus lambda B is also the element of S alpha for every alpha in I, and lambda in 0 to 1. Again, since this element lies in all alpha, on all the S alpha, so lambda A plus 1 minus lambda B lies in intersection of all S alphas. So alpha is, so again, what we have shown? We have shown that for every A and B in S alpha, intersection of this family, and lambda lies between 0 to 1, lambda A plus 1 minus lambda B is also in the intersection of family of these sets. So we have, so this is the definition of convex set. So S alpha is also a convex set. Again, we have theorem. Let X be a convex subset of Rn, and Y be a convex subset of Rm, where Nm are positive integers. So X cross Y is the convex subset of Rn cross Rm. So proof is very simple. Let A equals to x1 comma y1 is the subset of x cross y, and B is the element of x cross y, sorry, x2 comma y2 is the element of x cross y. So since lambda x1 plus 1 minus lambda x2 is the element of, and lambda y1 plus 1 minus lambda y2 are the element of x cross y. So lambda x1 plus 1 minus 1 minus, so lambda x1 comma y1 plus 1 minus lambda x2 comma y2 is the element of x cross y. Again, we have shown that lambda a plus 1 minus lambda b is the element of x cross y. Thus we have shown that for every a and b in x cross y, and lambda lies between 0 to 1, lambda a plus 1 minus lambda b is also lies in x cross y. So x cross y is a convex set. So x cross y is a convex set. Again, we are going to state some theorems, but the proof, we prove these theorems in next videos. So what are the theorems? The theorem is the interior of convex set int x, denoted by int x, is also a convex set. Convex set where x is the subset of Rn. Again, the closure of a convex set x bar is also a convex set of Rn. X is the subset of Rn.